Dr. Binz, who is speaking on the collision of Andromeda and us. So,
good afternoon. So I just want to say I got involved in making this talk, and it's probably an order of magnitude too long, too much detail. So I'll try to skip over some of the details, but if I skip over something that you think would be interesting, please feel free to ask. I don't want to skip over something interesting and talk about something you're not as interested in. So just ask questions if you have them, and I'll do my best to answer them. Of course, astronomy is a gigantic topic in more than one way, so I may need some help answering the questions. So first, though, I want to let you know something related. There's going to be a partial solar eclipse here in the valley tomorrow. About 4:30 or 4:40 p.m., about 50% of the sun will be covered by the moon. Dr. Ostalis is going to be providing telescopes with appropriate filters and safe viewing glasses at the planetarium from 3:30 to 5:30. So if you want to see the solar eclipse without going blind, that's one very good option. So even during full solar eclipses, it's not generally safe to look at the sun, so please do not look directly at the sun for any reason. Just want to put that disclaimer in there. I don't want to accidentally blind anyone. So tomorrow, 3:30 to 5:30 at the planetarium. So if you heard my talk last year, you may notice a trend here. I started last year's talk with a quote from Randall Munroe as well. But this year, the quote is, "If I added a 0 to this number, would the sentence containing it mean something different to me?" If the answer is no, then maybe that number has no business being in that sentence in the first place. So I put this quote up there, which is rather dangerous because I'm about to talk about astronomy, things that deal with stars, galaxies, the universe. And all of these numbers are enormous. In physics, we deal with distances from 10 to the negative 20 meters all the way up to 10 to the 25 meters? Yes, 10 to the 25 meters. So the size of the universe is about 10 to the 25 meters. We've narrowed the size of the electron to less than 10 to the negative 20 meters. Our society, our civilization runs on electrons, and we still haven't detected its size. So that's 45 orders of magnitude in size. And we only really have a good feeling for 6 or 7 of those orders of magnitude, somewhere around the 1 meter mark. The meter stick in this room happens to not be a meter long, but a meter is about 10 centimeters longer than this. It's about 10% longer than this. So we have a good idea of what that is. But anything much further from that, 5, 6, 20 orders of magnitude from that, we don't have a good feeling for the number. So I am going to attempt to give you some grounding, give you something to relate to these numbers to. So it's not just that, oh, hey, that's another big number. He said a big number. Good job. So hopefully it'll have a little bit more extra meaning. So we're going to talk about the broad cosmic structure, just to give you an idea of what we're talking about here. Of course, the goal of the talk is to talk about galaxy collisions, 2 galaxies colliding. So we're going to tell you what a galaxy is, talk about collisions in general, and then talk specifically about Andromeda and the Milky Way, the 2 galaxies that will be colliding. Of course, we are in the Milky Way, so this could have some repercussions for our life here on Earth. So our cosmic address. So normally you put your name first, you put your street, then city, state, and country. Of course, we're not worried about, on the intergalactic scale, we're not worried if it gets to the right country. If it gets to Earth, we're happy. So the first line of our address is Earth. And I put in quotes, tiny blue dot. In our normal lives, we think of the Earth as being large. How long would it take you to walk around the Earth? A long time. So it's pretty big compared to us, but in the grand scheme of things, it is an extremely tiny blue dot. The Earth is in the solar system, along with 7 other planets and the sun, and countless asteroids and dwarf planets and comets. So here is pictured the planets, Mercury through Neptune, and these are all to scale. The sizes of the planets are to scale. But the distances between the planets is not to scale at all. Not even close. Saturn is about twice the distance from the sun as Jupiter, and Uranus is again about twice as far from the sun as Saturn. So the distance scale here is not right, but the relative size of the planets is right. The sun doesn't even fit on the picture. We only see a small fraction of it. It is much, much larger than the rest of the planets, The sun is, by mass, 1,000 times larger than all the planets combined. More than 1,000 times larger. So it dominates our solar system. Our solar system is in a galaxy, and we call that galaxy the Milky Way. And here is an artist's rendition of the Milky Way. Why do we not have a picture of the Milky Way? We're in it. You can't take a picture of this building from this room, right? You can take a picture of part of the building out the window. So we can't see part of the galaxy, but we can't get a picture of the whole thing. And as such, we don't even really know for sure if it looks exactly like this. It's a spiral galaxy. It has this general shape. There's a bar. But the exact details are still unknown. We could, of course, send a satellite straight up. So Earth is somewhere around here. We could send a satellite up here to take a picture, but that would take a long time. So the Milky Way is in a local group of galaxies. So here is just a quick map of the local galaxies. Most of them are pretty small. The two largest ones are the Andromeda and Milky Way. So they're the two largest galaxies in our local group. The local group is in a larger collection of galaxies. If I'd given this talk last year, I would be saying the Virgo supercluster at this moment. But in September, I believe, a paper was published in Nature that suggested the Virgo supercluster is in an even larger supercluster. And that is what I'm going to be referencing. So I will let the authors themselves give the talk about the supercluster that we are in. Hopefully the volume works.
The third rock from the star called the Sun, just one of billions of stars in the spiral galaxy known as the Milky Way. But where in the universe is the Milky Way? A team of scientists gathered data on more than 8,000 of the galaxies that surround us. They mapped each galaxy's position and movement in space. And, for the first time, they've shown that the Milky Way is part of a much larger system of galaxies. A supercluster they have named Laniakea. The Milky Way is nested in the furthest reaches of the structure, on the outskirts. The entire universe can be seen as an intricate network of galaxies, a cosmic web. Some areas are almost empty, dark voids. Others are densely packed with galaxies in regions known as superclusters. Superclusters are the biggest structures found in the universe, but scientists have struggled to define where one ends and another begins. To map our home supercluster, a team led by Brent Tully at the University of Hawaii studied the motions of the galaxies around us in unprecedented detail. Even though the entire universe is expanding rapidly, gravity is also at work, pulling against this acceleration. Discounting cosmic expansion, the team worked out which galaxies are being pulled towards us, shown in blue, and which are being pulled away, shown in red. This enabled them to create a map of cosmic flows, the paths that galaxies migrate along, tugged at a tiny pace by the force of gravity. Using this motion, they came up with a new way to map the distribution of matter in the universe. Delving into our home supercluster, you can see that most galaxies are being pulled towards a dense centre. This is known as the Great Attractor. Our galaxy is among those sliding towards this patch of space, which dominates our region of the universe. Let's take a different view. Each circle represents a galaxy. Again, we can see most galaxies being pulled towards the Great Attractor, in the direction of the arrows. Between the Great Attractor and us, the Milky Way, is a relatively empty area, a blue void. And next to us is Virgo, a large and dense cluster whose bright galaxies have been observed from Earth for centuries. Until now, astronomers grouped us, the Milky Way and its surrounding galaxies, with Virgo and nearly 100 other clusters in a supercluster that stretches 100 million light years across. But using this new technique, we can see that this is just the tip of the iceberg. This cluster of clusters is merely an appendage of a much larger supercluster, more than 100 times bigger and more massive. How did the team know how to redraw the boundaries of this cosmic map? Here's our supercluster in black and a neighbouring structure, Perseus Pisces, in red. Scientists define the boundary as the points where the flows of galaxies diverge, like water dividing at a watershed. This is where neighbouring structures shear apart. This is the first clear definition of a supercluster. Laniakea means immeasurable heaven in Hawaiian, a fitting name for the vast community of galaxies that we are a part of. So now we know that on the edge of a supercluster called Laniakea, in a galaxy called the Milky Way, around a star we call the Sun, there is a small blue planet, our home.
Thanks. So that's the overall structure of the universe and how we fit into it, and very briefly. So galaxy. What is a galaxy? Well, it's a collection, island of stars in space. Galaxies tend to have between a few hundred million and a few trillion stars. So trillion is one of our first large numbers here, a trillion. 10 to the 12th. And just to try and give you some idea of how large that is, a trillion meters is how much we travel on Earth around the sun every year. So as we travel around the sun, it's about 1 trillion meters. So a big number. I wish I had $1 trillion, but it's almost ignorable in the context of the rest of the talk. So galaxies often also include not just stars, they're black holes, and there's lots of gas, dust and gas in the galaxies. Black hole, won't mention it much later in the talk, but at the center of every galaxy is a supermassive black hole. Black hole is named as such because it appears black, because it's so massive, the gravity is so strong that not even light can escape. So they're very large objects at the center of the galaxies. So galaxies have some general shapes. According to Hubble, an astronomer, the Hubble the man, astronomer lived in the early 20th century. He came with this pattern. There are spiral galaxies, the ones on the right, and then they head off into elliptical galaxies on the left. Some spiral galaxies have bars, those are the ones at the bottom, and others do not have bars in the center. They just go straight into the spiral. So the shape of these galaxies depends upon the cloud they formed from, the cloud of dust that they came from, as well as their past history and their neighbors. So if there was a galaxy nearby, it might have affected the shape of a galaxy. So we can tell a lot about a galaxy's history just by looking at its shape. So if we want to see some more examples of galaxies, we can look at the Hubble Extreme Deep Field. So Hubble, they pointed Hubble at a more or less barren part of space. Just look out. There's not many stars in the foreground. It looks black to us. They pointed it there for 23 days. And just to give you some scale, this is the patch of sky that they're looking at in terms of size. Here is the moon, also to scale. If you put your hand out, so arm's length away, the moon in this picture is about half the width of your finger. So the moon is pretty small, and then this is even smaller. For those of you that are familiar with degrees and arc minutes, it's about 2 arc minutes by 2 arc minutes. So it's a pretty small area. And this is what we saw. There are some stars in the foreground. So this is a star, you can tell because it's got the, can't think of the name right now, but it's got the spikes coming out of it of different colors. There's a couple stars in here, but everything else is a galaxy. So there are about 5,500 galaxies in this view. And we estimate that there are about 200 billion galaxies in the observable universe. So this is just a small fraction of them. And you can see there are spirals here. That's probably a spiral. We're seeing it from the side. And then there are also elliptical galaxies here. So 5,500 examples of galaxies. They didn't point it there for 23 days straight. They did it piecemeal over over many years. So what the galaxies are, let's talk about collisions. So with the vastness of space, you might think that galactic collisions would be very rare. But as we said earlier, galaxies tend to be found in clusters. So if the galaxies are grouped together, they're closer together than they would than the average distance is between galaxies. So they're more likely to collide than you might think, because they are closer to each other than you might think. About 1% of all galaxies are currently in the process of colliding. So if we look up, take a picture of an area of sky, about 1% of the galaxies in that picture will be undergoing some sort of collision. And we believe that about 10% of all galaxies have undergone a collision in the past. So the galaxies tend to be a little closer because they clump in clusters than you might expect, but also gravity. It's not like these galaxies are moving off in their own directions, in their own random directions. They're feeling the force of gravity of the other galaxies. And that force of gravity, just like on Earth, is pulling the galaxies together. And so they do a dance about the common center of mass until at some point they likely collide. And down there at the bottom is just the formula for gravity that Newton came up with. G is just a constant. But the larger the mass, the larger the force of gravity it feels. And then the further the objects are away, I don't think the mouse pointer is supposed to be part of that. The further they are away, the weaker the force of gravity. So it's not a linear thing. If you double the distance between two objects, the force of gravity goes down by a factor of 4. And that will be an important factor later on. So the results of galaxy collisions, they're really varied. It depends upon a lot on how the two galaxies first interact, their relative velocities, what parts hit first, what they're made out of. Is it mostly gas? Is it stars? But one thing is for sure, they always involve an enormous amount of energy. Energy and angular momentum can be ejected from the system along with mass. So when we collide with Andromeda, there's a possibility that the sun and the planets will be ejected from the resulting galaxy and just drift in open space. The gas content of galaxies can be pulled in any direction. It can be pulled between the galaxies as they interact. It can be left more or less in place, or it can even be dropped behind and trail as a tidal tail. So it all depends upon how these galaxies are shaped to start with and how they interact. Many collisions lead to a complete merger. So once they collide, they're likely to merge and become a single galaxy. And many induce starbursts. So a starburst is a rapid creation of stars. So a lot of stars are created all of a sudden. So to give you some perspective on this, Milky Way produces about 3 new stars a year. So Milky Way has about 300 billion stars in it. And 3 new ones are created each year. But in a galactic collision, several hundred new stars can be created every year. And is a volume much, much smaller than the Milky Way. The radius is 50 times smaller. What's 50 cubed? 625, 6 million? No. Anyway, 625,000 times smaller than the Milky Way. And the result of this collision is often an elliptical galaxy. So we start with this nice tight spiral, not unlike a Frisbee, nice tight spiral. And when the two galaxies collide, essentially chaos ensues and the stars start taking much more varied paths around the supermassive black hole at the center. So just how much energy? And this is just an off-the-cuff number, but about 10 to the 53rd joules. This is the largest number in the talk, thankfully. But 1 followed by 53 zeros joules. That's an enormous amount of energy. And this is just an estimate. But to try and give you some sense of what 10 to the 53 joules is, well, it's 10 to the 38 hydrogen bombs. So you can imagine what would happen to Earth if we somehow manufactured and then detonated 10 to the 38 hydrogen bombs. But again, this number is way too big. Does it really matter if it's 10 to the 38 or 10 to the 39? No, the Earth is gone either way. You laugh. What's wrong with you? So a more productive way to think about this is it would power human civilization for 10 to the 22nd, not 10 to the 22nd years, but 10 to the 22nd current age of the universe. So we could replay the current age of the universe 10 to the 22nd times before we ran out of energy. And the current age of the universe is about 14 billion years. So we could find some way to harness this energy, we'd be set, to say the very least. Again, but 10 to the 22nd, it's pretty big. So when stars reach the end of their life, they go through a spectacular explosion, and that's called a supernova. And that's about 10 to the 8th supernovas. This is 53 million joules, 10 to the 8th supernovas. Still a really large number. And just to give you an idea of the destruction and the power of supernovas, if a supernova went off 3,000 light years from us, it could still kill us. Could still cause a mass extinction here on Earth. So light year, what's a light year? So light year is the distance that light travels in a year. Light is the fastest object, if you will, in the universe. Nothing can go faster. It is what? About 10 to the 16 meters. A light year is about 10 to the 16 meters. So a supernova can be 10 to the 19 meters away and still kill us when it went off. So that is an enormous, again, still an enormous amount of energy. Make sure I got that right. Oh, yes. Okay. So light year is about 10 to the 16 meters. Again, big number. What does that really mean? Well, if you wanted to travel a light year here on Earth, you would have to go around the Earth 200 million times, which would take you about 1 million years on a passenger jet. And a military jet wouldn't save you much time. Even if you cut the time by a factor of 10, you're still talking 20 million years. Or we can talk about how many times around the sun. So 10,000 times around the sun at Earth's orbit is a light year. Of course, we don't have to do any work for this, which is great. We just have to sit here and live for 10,000 years. But that'll happen in about 10,000 years. 10,000 years is also a pretty big time. I mean, here in this country, we've only been around for a couple hundred years. What does 10,000 years mean? Well, in 8,000 BC, we were figuring out agriculture. So think of where we'll be by the time we've traveled another light year around the sun. All right, so supernovas, also very energetic. It only takes 10 to the 8th of them. So Einstein told us that E equals mc squared. We can convert energy to matter and vice versa. We haven't figured out all the details yet, but 10 to the 53 joules would be enough energy for us to create 1 million sun-sized stars out of nothing but energy. Just take the energy, poof, you get 1 million sun-sized stars. So this is the first number where I feel, okay, I know what 1 million is. I have a sense of what 1 million is. But it doesn't mean I'm going to stop. It is enough energy to accelerate the sun to 10 nines and a 6% the speed of light. So that would be extremely fast. The velocity of the protons, we spent billions upon billions of dollars to accelerate protons, little tiny little things, to only 6 nines % of the speed of light. So that is extremely fast. So hopefully you have some idea what 10 to the 53 joules means now. So collisions. What does exactly do the collisions look like? So I've got 2 videos that will show just generic simulated collisions. Thank you, Gia. So 2 galaxies. This is going to flash between a simulation and things we see in the sky. So this is an actual image that a telescope has taken, and it matches with this simulation. There's 2 spiral galaxies colliding. So it's rotating around to match the real world picture. Colliding also matches real world picture. So all those little dots are stars. Right. Got another one. Just note that as they collided, it didn't seem like much happened until they tried to pull apart. But certainly what was once two orderly spiral galaxies is now a giant cloud of stars going in various directions. So it started with two spirals and ended up with an odd amorphous shape, something like an ellipse, elliptical shape. Oops, that's not what I wanted. All right, so yeah, so again, as they come together, they seem to hold their shape fairly well until they start pulling apart. So they've collided now, but it doesn't look like it until they start to pull apart. Okay. So that's just some general characteristics of relatively random galaxy collisions. But we're here to talk about what's going to happen to Earth. So let's talk about the Milky Way. That's the galaxy we are in. It is about 110,000 light years across. So again, a number that's hard to understand. So let's say we had a light year's worth of meter sticks. So we had enough meter sticks to be a light year long. Its mass would be 10 to the 15 kilograms, which is about the same as the biomass of everything on Earth, the biomass on Earth. So if we converted every tree, every dead tree, every whale, deer, ant, we could probably leave humans out. We're a relatively small percent of the biomass. We converted all of that into meter sticks. It would be just long enough to be a light year. Humans are about 0.01% of the biomass, so we leave them off. It's fine. We'll only be off by a little bit in our measurements. But 110,000 light years is 5 orders of magnitude more than that. If we were to take, let's see here. So if we were to take all of those meter sticks, enough meter sticks to go 110,000 light years, and stack them all together in a sphere, it would be about 80% of the size of the moon. And it would be about 1/10 the mass. So it'd be 10 to the 21 kilograms worth of meter sticks. And if we put it up in the sky, it'd be just slightly smaller than our moon. So an enormous distance. So that's 110,000 light years across from here to here. The disk itself is about 2,000 light years thick. And these are abouts because we're inside the galaxy. It makes it relatively hard for us to understand what's going on. Again, while we're in this room, we don't really have a good understanding for how large this building is. We can look out that window and see that it goes down that way for a while, but we don't really know how far that way it goes. So this is just, but most buildings are rectangular or have built out of rectangular shapes. So we can estimate the size of the building based on what we can see. And that's what we do for galaxies, or for our galaxy. We can see a decent chunk of it, and we just assume, well, most galaxies we see are spirals. And we see that we are definitely in a spiral, so it probably has this general shape. So it's about 300 billion stars. Makes it a relatively large galaxy, but certainly not anywhere near the largest. And the mass is 10 to the 42 kilograms. I had a very hard time with this one. 10 to the 42 kilograms. It's not the largest number we're dealing with today, but the mass is just really hard to compare it to anything in our daily lives. So what I ended up doing was, let's say that every water molecule was 1,000 kilograms. Every water molecule is a ton. If that were true, then this amount of water would still be 30 kilometers cubed in size. So 30 kilometers cubed, that's about 15 miles cubed, give or take. So a pretty big volume. But still don't really have a good understanding of that number. So it takes about 14 years for that much water to flow through the Rio Grande River on average. So about 14 years worth of water through. And that's with the water being 1,000 kilograms per molecule. The chemist might correct me on this, but a water molecule is actually about 10 to the negative 28 kilograms. So to try to get this down to a time span we can understand, 14 years of water flowing down the river, I had to make the mass of water 31 orders of magnitude too large. So it's just an obscene amount of mass. That's all there is to it. Us, we're about here in this particular diagram, about 27,000 light years from the center. So we're about halfway out. If Earth had the mass of the whole galaxy, the acceleration due to gravity would be 10 to the 18th meters per second squared, which is 10 to the 17th more than it actually is. So not only would your mass be, your mass would be about 10 to the 29th kilograms, because water's so heavy now. But then gravity would be 10 to the 18th. So yeah, you'd be a pancake. So, yep. Okay. Andromeda. Andromeda's a little bigger. Its diameter is about 220,000 light years. So it's about twice as large in terms of radius as the Milky Way. It's about 1 trillion stars, so 3 times as many stars. It is about 2.5 billion light years away. And its mass is, about 3 times our mass, so 10 to the 42 kilograms, 3 times 10 to the 42 kilograms. But in the grand scheme of things, they're pretty similar. I mean, their mass is only off by a factor of 3. In the scales we're talking about, again, that's pretty negligible. So, got a video specifically about the collision between Andromeda and the Milky Way. So, Geo, please. Okay, there we go.
Astronomers have used the Hubble Space Telescope to forecast the future cosmic pileup, the titanic collision of the Milky Way and the Andromeda Galaxy in about 4 billion years' time. The Andromeda Galaxy, some 2.2 million light years away, is the closest spiral galaxy to our home, the Milky Way. For around a century, astronomers have known that it's moving towards us, but whether or not the 2 galaxies will actually collide or simply fly past each other remained unclear. Now, a team of astronomers has used the Hubble Space Telescope to shed light on this question by looking at the motion of stars in the Andromeda Galaxy.
Okay, we wanted to figure out how Andromeda was moving through space. So in order to do that, we measured the location of the Andromeda stars relative to the background galaxies. In 2002, they were in one place, and in 2010, they were in a slightly different place. And that allowed us to measure the motion over a period of 8 years.
The motion is actually incredibly subtle and not obvious to the human eye, even when looking at Hubble's sharp images. However, sophisticated image analysis revealed tiny movements that the scientists were able to project into the future. Based on these findings, it is finally possible to show what will happen to the Milky Way over the next 8 billion years. As the galaxies drift closer, and gradually merge into a single, larger, elliptical galaxy with reddish stars. And yet the solar system should in fact survive this huge crash.
No, the reason we think that our solar system will not be much affected by this collision between the Milky Way and Andromeda is that galaxies are actually mostly empty space. Even though our galaxy, as well as the Andromeda Galaxy, has 100 billion stars in it, they're very far apart. So if two galaxies actually collide with each other, the stars basically pass right between each other. And the chance of two stars directly hitting each other is really, really small. So the likelihood that our solar system will be directly impacted by another star, for example in Andromeda, as we collide with it, is really, really small. Well, if life is still present on Earth when this happens, the changes in the sky will be quite spectacular. Now, they will be very, very slow, because the time scales on the scales of galaxies in the universe are very, very long. So you have to think millions of years. But even then, over these time scales of millions of years, we will see big changes. If we wait a few billion years, Andromeda will be huge on the sky. It will be as big as our Milky Way, because we'll be very close to it. And then later, when the galaxies merge, the merged remnant of the Milky Way galaxy and Andromeda will look more like an elliptical galaxy. And we will be sitting right in it. So the view of the Milky Way on the night sky will be completely gone. And this band of light will be replaced by a more spheroidal distribution of light.
And so the Sun, born in the Milky Way almost 5 billion years ago, will end its life in a new orbit as part of a new galaxy.
So we could trust the people from NASA that, oh, we're going to be safe. Or we can do a little back of the napkin calculation and determine it for ourselves. So they said that the stars are relatively far apart. So just how far apart are they, and just what are our chances? So a very naive approach. I'm going to look at the density of stars around us. So based on the stars we've seen, there's about 1 star per 284 cubic light years. So we talk about how big of a light year is. This is 284 cubic light years. This is an extremely large volume for every star. But, and I'm going to talk about just very quickly, if the two galaxies collide like this, so like pancakes, with the Milky Way coming down on top of Andromeda, our star is going to have to go through the disk of Andromeda. And that disk is, if it's similar to the Milky Way, about 2,000 light years thick. And during that time, it's going to have a chance to get close to quite a few stars. So if we look straight down, and I'm just using the Milky Way as an example because we know more about the stars around here. We look down at the Milky Way, there's about 1 star for every 0.142 square light years. So this 2,000 light year thickness has really helped increase the density at our parent density. We can also say that there's 1 star or 7 stars per square light year. So square light year is still a pretty big area, but there's 7 stars in there. So maybe the chances of us getting hit isn't so small after all. So again, if we're assuming that the two galaxies collide like pancakes and that the density of stars in Andromeda is about the same as it is around us, then as we go through, our sun will get close to about 7 stars. And comparing the density, 7 per square light year, to the size of the sun is about 700,000 kilometers in radius. Yeah, 696,342 kilometers in radius. So it's huge. But a light year is obviously much larger. And so we've got about a 10 to the negative 12% chance that 2 stars will collide with this very naive approach. So that's a really small possibility, not something we have to worry about. Even with billions of stars in the galaxy, hundreds of billions and trillions of stars in the galaxies, there's about a 0.1% chance that any of them will collide with these numbers. So we really don't have to worry about anything hitting our sun. Chances of it happening are essentially 0. But what if the sun hits us? Or what if the intruding star hits us? Or just gets close enough to fling us out of the solar system? How likely is that? So when I read up on this, everyone's like, oh, the chances of two stars colliding is really small. Well, I don't care if a star collides. Certainly, if a star collided with the sun, we would be in trouble. But that's not the only problem we have to worry about. So my question is, what happens if the star just gets kind of close? So I wrote a quick simulation. I'm going to show it to you in a minute. But on the left side, we're going to be looking essentially down at the solar system. Now, down is an odd concept in space, but we've defined it essentially as, so the Earth, we've got the North Pole. We say the North Pole points in the northerly direction in general. So when I say we're looking down at the solar system from above, I'm saying we're doing it from above the North Pole, essentially of the sun or the Earth. Doesn't really matter. So on the side, we're going to be looking down. Horizontal axis is X, vertical is Y. On the right side, we'll be looking essentially edge on in the solar system. It's not exactly edge on, because then you just see planets going back and forth. So it's a little tilted. But basically, the z-axis is up, and the x-axis is horizontal. So I'm going to start with just the solar system as it is. There we go. So I set the scale so that Neptune, you can just barely see it over here. Maybe it's dark blue. Just barely fits on the screen. And then you can see the sun is down here, and there are trails that map out where the planets have been. To get the trails visible, I had to double the width of the line in terms of pixels. And for whatever reason, that shifted them all a little off. So the sun is here, and the trails are showing up there. I apologize for that. But rest assured, that is not actually where the trails are. So we're looking down, and you can see red is Mars, and it doesn't look very circular. The main reason for this isn't the actual orbit, unfortunately. It's because we're going with a 16:9 resolution there, and the projector is squishing it to 4:3. So Mars's orbit is actually very close to circular. It's showing up as elliptical just because technology. And I apologize for that. Mercury's the only one with a really large eccentricity, so it's very elliptical. On the right, I've got the distance from the sun. So the sun is 0 meters from the sun. And then the velocity in kilometers per second. So the sun is going about 20 meters per second right now. Earth is going about 30 kilometers per second. So that's with no intruding star. The solar system does indeed work. If we let time go, we will soon find that the period of Neptune's orbit is exactly as we observe it to be. So we have to introduce an intruder star to see how it's going to affect things. What kind of star should we throw in? Well, big one. So I just went with one about the sizes of our sun. Smaller stars last longer than big stars, so chances are what's going to come by is a smaller star. How fast should it go? Well, the sun is moving about 230 kilometers per second around the center of the galaxy. 230 kilometers per second. So these aren't units we usually use. That translates to 515,000 miles an hour. You can go from Maine to San Diego in 19 seconds. Of course, if you did that, you'd be a puddle of goo, because you'd accelerate and decelerate so fast that your body would be crushed. Details. Andromeda is approaching us at about 110 kilometers per second, and will speed up as it gets closer. Just like if you drop an object from a building, it goes faster as it gets closer to the Earth. The stars in Andromeda are also moving. In fact, since Andromeda is more massive, there's a chance that the stars are actually moving faster. But certainly, the stars are moving in the 100 kilometer per second range, 100 to 600, somewhere in there. So I just went with 350 kilometers per second. There's no way to predict the actual relative velocities of the two, of the stars in the two galaxies. So NASA did their best job. They compared Andromeda's location 8 years apart. But as I said, they had to use special software to detect the distance. They couldn't even see the difference. So it's a really rough estimate about Andromeda's velocity and whatnot. So we have no real clue of how close it'll be, where it'll actually collide. We just think that at this moment it will indeed collide. So let's start conservatively. Let's put the star's closest approach to the sun at around 20 AU. An astronomical unit is the distance from the Earth to the sun. So we're basically saying this intruding star is going to be about 20 times further from the sun than the Earth. Hang on. So you can see the intruder star over here. It's going down into the solar system from here. That's why it doesn't appear to be moving. After a little while, it's going to appear up there in the numbers and then come straight down through the solar system. And since I do not want to wait, it's 350, Let's speed it up a little. I start to wonder, did I open the right one? There it goes. Sorry about that. So there it goes. The intruder goes flying through the solar system. You can tell it didn't spend much time in the area. It's going 350 kilometers per second. Saturn seemed to be affected a little bit, but not much. Uranus was the closest one to it, and you can't really detect any change in its trajectory. So we had a sun-sized object go straight through the solar system, and it appears to have done very little. In fact, you can see the red, the Mars path is wider than it was. The solar system is moving that way toward where that star went through at about 240 meters per second. But that was the only real change. Earth's orbit is still going between 146, 147 million and 151 million. It was changed ever so slightly, but it probably wouldn't be enough to really change much for us. Moved it no more than 0.5%. So apparently, if a sun-like star goes through at that speed, it's not going to do much to us. And we're running a little low on time, I'm afraid. So I'm going to skip the next simulation. That puts the sun go through it, or the intruding star goes through at 3 AU, so pretty close. Still, it doesn't have a huge effect. It's just moving too fast. So if we want to see some destruction, which I'm guessing you do based on how much you laughed when I destroyed the Earth earlier, let's skip to one of the later ones. So my solution was, well, what if the star is going more slowly? So 50 kilometers per second. It's going to take you, gosh, almost 2 minutes to get across the country now. Tragedy. So I'm going to zoom in a little bit because the intruder is going to be closer. Going more slowly, so it takes longer for it to get into the solar system. Again, you'll see it go down vertically through the right screen. So, as the intruder star came down, the solar system went up to meet it. Gravity was attracting it upward and to the right because that's where it was. And you can see the tracks of the planets look really chaotic. But they are still, in fact, following the sun. So if I redo this simulation, zoom in again. This time I'm going to force the sun to stay at the center. So I'm going to keep our field of view looking straight at the sun. Intruder goes through. Of course, it's close to the sun. It gets pulled by the sun. It gets pulled that way. Wow. Whoops. That's going to hurt. But so this planet, this intruding star, went about 3 AU from the sun. This is about 3 AU from the sun. And if you look at Earth's orbit, usually the Earth goes from 150 million, say about 150 million meters from the sun. Here we're going from 100 million to 200 million. So during the 100 million time period, we're going to be a lot hotter. This is actually large enough distance to affect our seasons. Much colder, 200. We'd probably survive. I think we could probably still eke off some agriculture and get some food in the intermediate time. Certainly would not be particularly easy. But there's a problem. Jupiter and Saturn were pulled into the solar system. And at any time, I don't have collision detection here, but at any time these planets could swallow the Earth or knock the Earth out of the solar system. So this situation, the Earth's orbit was affected quite a bit, probably not enough to kill us. But over time, our orbit's probably unstable because Saturn and Jupiter are flying through. I'd like to note, The distances in this simulation, the physical distances are all correct. So if we go back, and I'm out of time. So the distances between the planets is right. Well, the planets are 5,000 times too big. I wanted you to be able to see the planets, so they're 5,000 too big for the distance scale. If they were the right size, they would all be smaller than a pixel and you wouldn't be able to see them. So just real quick, the summary is that if the star is moving as fast as I think it might be going, we're probably going to be fine unless it directly hits us or gets really close to one of the planets. But if a slower star gets within about 10 AU of the sun, Saturn and Jupiter have a decent chance of being flung into the inner solar system. So what are the chances of a star getting within 10 AU of the sun? That's about 10 times to the negative 6%. So still, nothing to worry about. So thank you for your time, and have a wonderful day.